Now we'll briefly look at the second law and its implications on the viscosity coefficients, where we return to the energy equation in this form. Remember, E is total energy. It's the material derivative of energy times the density of nabla dot K nabla theta, which is temperature, minus P, the pressure of the divergence of the velocity, summed with the density. Here, rho phi is the second coefficient of viscosity times the divergence of velocity field squared, plus 2 times the first coefficient of viscosity times the dyadic. Now, if we use the conservation of mass and substitute with the energy equation, we find this slightly different form, and you'll see why we do this in a second. Now we use the equation for entropy. Here S is entropy, so this is the conservation or increase of entropy equation with energy. If we substitute in 110 with this equation, then we'll find a balance of entropy equation in integral form. Remember, the omegas are volumetric integrals. S is the material derivative of entropy. What does this equation really show us? It shows us that the rate of increase of entropy is not less than the heat transfer into the material volume, or the fluid parcel. If we believe that the fluid is fluid perfect, like Leonhard Euler would say, then there's no heat conductivity. If there's no heat conductivity, and the viscosity, this equation will be reduced to 0, we'll find this equation, that the material derivative of the entropy is 0, which is good. It's a conservation of entropy equation given the fluid is perfect with no heat conduction and viscosity is 0. If we make the assumption of Joseph Fourier's law, then the second law of thermodynamics, 13, can be written in this nice compact form. K is heat conductivity, of course. Theta is temperature. Rho is density. Then it'll be greater than or equal to 0. This assumption means that there's particular restrictions on the coefficients of the Navier-Stokes equations, which is the big implication of this analysis. First, we'll say that if Fourier law holds, we must have the following restrictions on the coefficients. First, that the first coefficient of viscosity must be greater than or equal to 0. So this should answer the question of why we can never have negative viscosities, because it would violate the second law of thermodynamics. Also, the Fourier coefficient K, the heat conductivity coefficient, must be greater than or equal to 0. You can never have a negative one because it'll violate the same thermodynamic law. And finally, the relation between the second and first viscosity coefficients, lambda and mu respectively, must obey this law if Fourier law holds. And this is where these very important inequalities come from when you often see them in your introductory classes on fluid dynamics.